Let's refresh our memory on some conventional power systems. And from there, we can combine those conventional power systems to make them into what we know as a more efficient power system. This will give us a good background in order to develop upon so that we can then really understand the components and the processes in a combined heat and power system, which is also a high efficiency stationary power generation system. So let's remember a Rankine cycle. So a conventional power system, just a simple uh, basic power system, is built on a Rankine cycle, which you might remember from thermodynamics. And in the Rankine cycle, we have a boiler. So if this is our boiler, then we need to put heat into that boiler. And that boiler simply turns a turbine. And from that turbine, we can do mechanical work directly, or we can use that mechanical work to turn a generator in order to make electricity. So let's draw the components first. And then out of the turbine, we're going to condense, because in the turbine, so the steam that comes out of the turbine will be warm, not as hot as when it went in, but it will be warm. So then it goes through a condenser. And from there, it will condense into water, and it will then go to a pump, where the pump will pump the water back into the boiler in order for it to be heated again, for it to come out of the boiler, drive the turbine back to the condenser. So that's the full cycle. So now let's show where we put some work in. So we put heat in here. And it costs money to make that heat, right? And it possibly even burns fossil fuels to make that heat. Likely does. And then work has to be put into this pump, which also costs energy. And of course, we get work out, which could then go to a generator, turn the generator to make electricity. And that is how a conventional power system is set up, not a high efficiency power system. So there's another type of system that is conventional, and that's the gas generator. So in a gas generator, for example, the Brayton cycle, if you remember from thermodynamics, in a gas generator, you don't have to first burn a fossil fuel to make steam. You can burn the fuel directly. So in a gas generator, we had a combustion chamber, or a combustor. I like drawing it like this. So it's combusting. I'll call that a combustor. And then directly from the combustor, you would drive a turbine, but this one, in this case, it's a gas turbine. And out of that gas turbine, there's going to be byproducts. Those byproducts actually came from the combustion process. The purpose of this turbine is to drive this shaft, and this shaft in turn can be added and can be attached to a compressor. So the turbine is attached to a compressor, and air comes in the inlet of the compressor, gets compressed, and goes out. The air, so let's look at some of the inputs and outputs. The air is drawn from atmosphere. So that's okay. What you end up with going in here then is compressed air. And the reason you would need compressed air is that's your oxygen source. Of course, oxygen is required for combustion. What you need to add to your combustor is fuel. So that's where your cost is adding that fuel in. It's the cost of that fuel. And of course, work comes out of this gas turbine. And that work can do mechanical work right away, or it can be connected to a generator to make electrical energy. So that's another one of our conventional power systems. I think it's important to review those conventional power systems before we can investigate a combined cycle, which is the gas vapor cycle. And the gas vapor cycle is a type, it's not new, but it is a type of high efficiency energy system, power generation system. So the combined cycle is called a gas vapor cycle. The gas vapor cycle essentially combines the two cycles we just did and makes one system that is more efficient because it uses the heat that comes off the gas turbine in order to make the steam for the steam turbine. So let's draw the system that we just had, where we had this combustor. And there's the flames. And the combustor went into a gas turbine, didn't it? And that gas turbine spun a shaft to make a compressor work. The compressor brought in air in order to feed oxygen to the combustion process. We put fuel in. That is a cost. Now, instead of byproducts of combustion coming out here, we're going to use that. Of course, there are still byproducts in it. It doesn't make it clean, but we're going to use it and we're going to put it, this is the new part of the system, and it's a heat exchanger. And that heat exchanger is going to take some of this heat from the the outlet of the combustion process, the outlet of the gas turbine. And then, of course, over here, you still do have the byproducts of combustion. And now you have this heat. And from the heat, we can make our other cycle that went to our Rankine cycle that went to a steam turbine. Because now we just use this heat out of the gas turbine to heat up some steam. Well, how do we have steam in there? Well, we'll have to stick some water in there. And how do we get water in there? We need a pump. Where do we get the water from? it must condense. And it condensed from the outlet of the steam from the steam turbine. Now let's look at where we get some work. Of course, we got some work out of here from our Brayton cycle, and then we got some work out of here from our Rankin cycle. And the work here must be less than the work from Brayton because, well, obviously you can't make more work from the leftover energy that came out of that gas turbine. You also get some heat out of the system. So this is how a high efficiency gas vapor cycle power generation system works. And this is fundamentally important to understand before we develop CHP systems in class.